Okay, so a few announcements. First of all, I had gotten a few emails about Chem 101 over the weekend, and I wanted you to pay attention to, sorry, get my frame of thoughts back. I had put the wrong time for the due date. You should be able to do things late, and then once you let me know that I have the time wrong, it'll adjust and take away the late penalty. But I've moved the due date to today so that if you didn't get it done yesterday, because you had seen that the time had run out, that you have that opportunity. But generally, just go ahead and do it, and then once I move the due date, it'll remove the late penalty. The other thing was a couple of people were having trouble with the dot structures. It gives you a circle to begin with, and you adjust the number of dots and the number of bonds, but you need to replace the circles with the elements. And you do that by clicking, it looks like a little periodic table on the bottom, and it says change element. So that's how you're going to change that element. So I have posted a new homework assignment that includes resonance structures and formal charges. I don't think we're going to get to formal charges today, but this isn't due until Thursday. So we'll go over formal charges on Wednesday. I will have a prepare to learn, but that's not going to be over the formal charges. That'll be over the last couple of sections. So that will be over section 5 and 6. So section 4, there's no prepare to learn over, but do go ahead and read it because it covers resonance, which we're going to talk about today and will be on your quiz, and covers formal charges, which will not be on your quiz. Then you have a quiz on Wednesday, and obviously if you have a prepare to learn over it, you need to be reading section 7 and 7.5 and 7.6 for Friday. So first thing to do is just kind of look over it, see what it's about, and then answer the prepare to learn questions about it, and then look at it a little bit more intensely as we're going through that material so that you understand it a little better. Any logistical questions? Okay, I would like for you to start by trying to draw these dot structures so that you have an opportunity to try that out, and I will come around, and if you have questions about what you're supposed to do, how you're supposed to get the number of valence electrons, if you get stuck, you can flag me down and I can answer those questions. I've seen water looking like this, like it's a straight line. I've also seen water looking like this, so that it's bent. Either one is an appropriate dot structure. Does anybody know, is water a bent molecule or straight molecule? It's a bent molecule. But remember, our dot structure isn't showing us the geometry, because even our bent molecule here looks like that's a right angle, a 90-degree angle. It's actually wider than that. So it's important to remember when we start talking about the three-dimensional geometry of the molecules, you can't just look at the dot structure and say, oh, that looks like this shape, because I can't always represent in 2 dimensions what something looks like. All right, so we also had H2O. When you are looking at a molecule and you want to know what to put in the middle, the first element and the one that's farthest from fluorine are the ones that go in the middle, unless we have our problem child hydrogen. So for H2O, you can put hydrogen in the middle because it can only have one bond. But in this case, the carbon is going to go in the middle. And put the other elements around it. And then you might have done this and said, oh, well, that looks good. And that also has, let's see, we had 4 plus 2 plus 6, that's 12. That has 12. What's wrong with this structure? What? I'm missing electrons. Okay, it has the right number, but if I look at carbon, does carbon have an octet? No. So if I complete the octet, then I've got too many electrons. So I need to move those electrons to form a double bond here. So I'm going to get rid of a pair here and a pair here and form a double bond. Okay. So if I need more electrons to complete the octet that are available to me, that's when I'm forming multiple bonds. All right, you had nitrogen as a molecule. That's one of our diatomics. Should have ended up looking like this. And you had carbon monoxide, should have ended up looking like this. And then last week, we also did cyanide, which ends up looking like this. We'll put a little charge there for it. So each of these has 10 electrons. Okay, does anybody need to see how we get to that structure? Okay. So let's take a look at the carbon monoxide. With 10 electrons, I start with carbon and oxygen. Complete the octet. And I count 2, 4, 6, 8, 10, 12, and this line is 2 more. So I have 14. So that's too many electrons. So I remove a pair from each of these atoms and replace that with a bond. And then I go 2, 4, 6, 8, 10, 12. I still have too many. So I'm going to remove another pair from each atom and replace it with a bond. And if that's too messy looking for me, then I write it over without the X's on it. And that's what I'm doing. Okay. Remember, I'm getting my count, my 10 electrons, by looking at how many valence electrons does carbon have, or how many does oxygen have? 6. Does anybody need help remembering how to get to the valence electrons? Excellent. Okay, so these that all have 10 electrons are what we call isoelectronic. So when I'm talking about atoms or monoatomic ions, I mean the total number of electrons. And I usually mean that for molecules too. So if I'm looking at, let's say, neon, it has the same number of electrons as chlorine minus and O2 minus. This has 10. Chlorine has a valence count of 9 plus 1 electron. Oxygen has neon has 8 valence electrons, 10 total. Chlorine has 9 electrons total plus 1 electron. Oxygen has 8 total plus 2 electrons. Those all have 10. Okay, so those are isoelectronic, and they are isoelectronic with sodium plus. So sodium has 11 electrons, but I take 1 away. Okay, so that's what isoelectronic means. That means that if I'm writing the electron configuration, they are all going to have the electron configuration that looks like that. For a molecule, we usually are just kind of looking at the outside of it to say that is isoelectronic. But a lot of times people will also say, no, it needs to be, you know, the same 2s and not a 2s and a 2p kind of thing going on. But these are isoelectronic because they have the same total valence electrons. For a molecule, valence electrons. So anytime I have 2 atoms with 10 valence electrons, it's always going to end up looking this way. That's why it's useful to know when things are isoelectronic. All right, this is a little bit out of order from your book. We haven't hit the exceptions to the octet rule, but I like to hit resonance first because it fits in with the things that don't object to the octet rule. So resonance, let's look at an example of it, and then you'll kind of be able to understand the definition a little bit better. If I look at a nitrate ion, so nitrate is what formula? NO3 with a -1 charge, okay? If I'm trying to draw that dot structure, I'm going to end up drawing a dot structure with 1 double bond and 2 single bonds. So the question becomes, how do we know which one has the double bond? So this is one example of what we might draw. And we should have the charge on the outside. I think appears on the end of this row of things. So does it go on this first oxygen or does it go on one of the other oxygens? I guess I didn't put the charge on. So I'll leave it there. Okay, what did I just do? I don't know. Computer thing, not a screen thing. Is the power out? Aha, okay. Okay. So we can draw these different structures. Any one of them would be correct. When we want to illustrate that something has resonance, what we do is draw a double-headed arrow in between the two. So remember when we talked about dipoles, I said how to draw an arrow is important in chemistry. So this double-headed arrow specifically means resonance. It specifically means that both of these forms are correct. And you can kind of think of it as being like it goes back and forth between these two. In reality, electrons move so quickly that what we observe when we're trying to measure the lengths of the bonds and we're trying to measure the energies of the bonds is that all of the bonds, instead of looking like there are 2 single bonds and 1 double bond, they all look like they're sort of in between the two. So sometimes what we'll do is draw a structure with a single bond and then a dotted line to show that there is at least 1 bond and then something in between that single and double bond. So sometimes you'll see it like this. This isn't very illustrative of how strong that bond is. We don't know if it's 1.5 or 1 1/3 or 1 3/4. So usually it's preferable to draw the structure, one of the resonance structures, rather than drawing this in between. But you'll sometimes see it drawn this way just to emphasize that we don't really have a difference between the bonds. So the answer to the question, no, they're not truly 1 short, strong bond and 2 long, weak bonds. So in reality, each bond in a resonance structure is intermediate between a single and a double bond. Now this can also be true if we have triple bonds in the picture. I'm just using the terminology right now as if it was between a single and a double bond. So how do we determine the bond order? So remember our bond order, we said a single bond is 1 and a double bond is 2. The reason we use the numbers instead of saying single and double bond all the time is that if we have this intermediate thing, what do you call something intermediate between a single and a double? That gets really cumbersome. But we can apply a number to it. So it works out to be 1 1/3. All right, how did we get there? So we had our structure that was something like this. 1 double bond and 2 single bonds. So count bond lines or find the total bond order. So I have 1, 2, 3, 4 lines, or I could add a single bond plus a single, plus a single bond plus a double bond. That gives me 4. And then I divide by bonded atoms. Don't count the central one, okay? So I have 1, 2, 3 oxygens that are bonded. So 4 divided by 3 is equal to 1 1/3. That's how we came up with that. What are the resonance structures of ozone? So what I'd like you to do is first try and draw a structure for ozone. Ozone is 3 oxygens, each of which is neutral. So we should have a total of 18 valence electrons. Anybody not sure where I got that from? Okay, so what we do for each oxygen, we find it on the periodic table and determine its valence electrons. So for oxygen, it is in the second row, I start counting the elements: lithium, beryllium, boron, carbon, nitrogen, oxygen. It is the 6th element, so it's 6 valence electrons. And since there are 3 of them, that becomes 18. This is my structure. Is that what you came up with? 1 single bond and 1 double bond? So if I started out with just single bonds and put dots all the way around, I would have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. So that's too many. So when we have too many dots, we take away a pair on the central atom and a pair on the outside atom and replace that with a bond. Okay? So I can tell that this has resonance because I have 2 outside atoms that are the same element but have different bonds. So that means that I had to make a decision about which side was going to be double bonded and which side was going to be single bonded. So I show that resonance with this double-headed arrow. I'm going to have this light. And then I redraw it with a double bond on the other side. Right? So what would be the bond order, the true bond order of the bonds in ozone? Determine that using our rules up above. All right, anybody want to volunteer a guess? Anything? 3 halves, yeah. So we have 3 lines or a total bond order of 3. And then we have 2 outside atoms. So it's 3 halves, or if you said 1.5 or 1.5, all of those would be different. Okay. Okay, so the first one we already know about. Hydrogen only forms 1 bond. So this isn't anything new, so I'm not even going to say much about it. Cations and electropositive atoms can be electron deficient. So I'm going to give you examples of this, but this isn't something that comes up a whole lot in chemistry, so we're not really going to focus on it. So as I said with cations, we don't show the dots on there. We don't have 8 dots around them because they have lost everything from their valence shell. Okay, so cations don't have it. But we also have examples of elements that are non-metals or semi-metals that that can covalently bond, but they don't end up with an octet. And so those are the A's and the B's. Aluminum, boron, and beryllium are the three that you'll see listed. So remember that while we technically, or while we describe a covalent bond as always between two nonmetals, technically it has to do with the electronegativity difference. And so if I have one of those elements attached to something that is not as electronegative, it can be kind of a covalent bond. But they tend to only form a bond with each of their valence electrons. So how many valence electrons would boron have? Has 3. So it tends to form only 3 bonds, and then it doesn't have any lone pairs. So if it's forming 3 bonds, then it only has 6 electrons around, okay? So we call that electron deficient if it doesn't quite have as many. And the only elements that you will see that do that are the A's and the B's, aluminum, boron, and beryllium. Right? There are others that would potentially do it, but you won't see those as examples, so don't worry about it. I'm going to skip over that, but there's beryllium, boron trifluoride. And so we said that with ionic bonds, there's some covalency. So even though beryllium is technically a metal and boron is a semi-metal, they're not truly ionic interactions. There isn't really such a thing as a beryllium 2+ cation. We can't separate that out from other things the way we could with sodium chloride by dissolving it in water. They're all electropositive, which means the number for their electronegativity is fairly small. And so they don't really have a need to have those electrons in their octet. So the main thing you need to know is what do we mean by electron deficient and which elements are you apt to see in it. Okay. If I have you draw a dot structure, usually you will either have an octet. That's always the best way to go. Try and make an octet for every single atom, except for hydrogen. Or there will be an expanded octet. That's the other one. All right, so this is the big one that we will see lots of. Expanded octets happen when our principal quantum number, so remember N was the principal quantum number, and that tells us the energy level, but it also kind of tells us which row we are in the periodic table. So row 3 on the periodic table, we have the 3s and the 3p orbitals, and that's where we find sulfur, phosphorus, and chlorine. Those elements and anything lower on the periodic table can have an expanded octet. Okay. So we have those 3d orbitals. They're not filled with electrons, but they're hanging out nearby to where the electrons are. So the explanation that is often given is that they're low enough in energy that they can be accessed. That means that they can kind of borrow those orbitals to do a little bit of fun. And what they find, or they're not really searching for anything, they're just facts. But what happens is that in using those orbitals, the whole molecule is lower energy, more stable. And more stable means less likely to change. More stable is lower energy. So the lower the overall energy of the molecule is, the more stable it is, the more likely we are to stay at that energy level. So this is kind of the explanation for why this happens and why it only happens for level 3 and below, because there's no such thing as a 2d orbital. So our elements in row 2 don't have those d orbitals nearby that they can access for this. Right? I'm not going to ask you to recap the explanation, but you do need to know which elements can do this, because if you start forming an expanded octet for carbon or oxygen, I'm going to count it wrong. All right, does anybody need me to wait on this slide? Okay. So given the information that we have, we want to know which of these has an expanded octet. So sulfur can always have one, but it doesn't have to have. So what we would do for each of these is try and draw the dot structure and see if we are forced to have an expanded octet. Well, one way to know right off the bat is that if I have more than 4 things bonded to the central atom, it automatically has to have more than 8 electrons, right? Because each bond is 2 electrons. So that letter D, SF6, that has to have an expanded octet. Does that make sense? Since the sulfur is bonded to 6 things, automatically it has 6 times 2 or 12 electrons around it. Okay, so one of the things that was on there was SO2. Well, sulfur is in the same row as oxygen, not row, column as oxygen. And so it also has 6 valence electrons. So this structure is going to look a lot like the ozone. So I count up these. I have 6 plus 12 is 18 electrons. My first element goes in the middle. I bond it to each of the side elements. And I place dots around to finish the octet. And then I count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have too many electrons. Cross out a pair on my central atom, cross out a pair on my side, and replace that with a double bond. So it looks a lot like the ozone atom, or ozone molecule, okay? So in this case, our sulfur, if we count, has 3 bonds. So that's 6 electrons, and 1 lone pair has 8. So it's following the octet. Now if I have SH2, this is a little bit like water. I have 6 electrons for sulfur, 2 for the hydrogen, total of 8. And my structure ends up looking something like this. Or I could have the hydrogen off to the side. Now, since hydrogen can't form multiple bonds, this is really the only way I can do this. So the first one, SO2, has resonance, just like ozone did. The second one doesn't have resonance. There's only one way to do that structure, single bond to each of the hydrogens. Now, if I'm doing the SF6, I have 6 electrons for each of the sulfurs. How many for the fluorine? 7. Good. But there are 6 of them. Now I've got into the multiplication tables that I really struggled with back in the day. So 7 times 6 is 42, plus another 6 is 48 electrons. And so I might start with just the 4, 1 on each side. But our rule says put all of the atoms around the central atoms. So I got all 6 of them around there. I draw a line to each of those. That means I've got a single bond to each of them. That represents 2 electrons for each of those. And then I complete the octet. This can be a little tricky. Complete the octet around each of these atoms. All right, and then I count them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. 48 electrons. I check to make sure I have octet rule satisfied. I do for fluorine, which has to be, sulfur doesn't, but it's okay. Sulfur's allowed to have extra. Now, can sulfur have an electron deficiency? Can it have fewer than 8? No, because it's not an A or a B. Okay. All right, I'm gonna actually stick with this for a second. I just remembered the other thing I was gonna mention about Chem 101. When you are doing your dot structures on Chem 101, it has you put the number of electrons, the number of bonds, but it gives you these two circles. In the bottom, there's a little periodic table. You have to click on that and change this circle to whatever element it is. Otherwise, it's going to count it wrong. Just so you're aware of that. All right. This becomes important when we are talking about the resonance structures of things that would follow the octet rule, but don't necessarily. So let's take a look at sulfate. SO4 2 minus. So take a second to try and draw the dot structure for sulfate. All right, so you probably ended up with something very much like this. Hopefully you remembered to put your charge off to the side so you didn't lose some points on your quiz for that. So we would look at this and we would say, oh, it doesn't look like there's any resonance structures because all of the oxygens have the same bonding. They all have a single bond. But this molecule actually does have resonance structures. So we have a difference between equivalent resonance structures and non-equivalent resonance structures. So when we look at ozone, those were equivalent resonance structures because they had the same number of double bonds. The two different structures had the same number of double bonds, and the two different structures had the same number of single bonds. Now that doesn't mean that single bonds has to equal double bonds. It just has to be, as I count single bonds on each structure, it's the same. As I count double bonds on the structure, they're each the same. Okay, those are equivalent, which means energy-wise, the molecule can't tell the difference. But I can have non-equivalent resonance structures, and they're going to have a different level of stability. So in your book, it well, in Kim Skill Builder, I can't remember the book. I think your book does this. It shows you how organic chemists show electrons moving. So you go from the electrons to where they're moving, and you use a curved arrow. So I can take some of these electrons and have them form bonds. Okay, so I'm going to show a different resonance structure. So I'm going to ask myself, is this a valid structure? So a valid structure means I'm following the rules for a good dot structure, that I have to have octet rule satisfied for everything unless I have one of those two exceptions we talked about, expanded octet or electron deficiency. So each of my oxygens has 8 electrons, right? So it's satisfied. And the sulfur has 2, 4, 6, 8, 10, 12 electrons. So it's not satisfying the octet rule, but it's allowed to have an expanded octet. We saw with the sulfur hexafluoride that it happens. It turns out that this structure here is more stable. So when I have an equivalent resonance structure, they all have the same energy, which is our way of saying stability. Stability. For non-equivalent, I have different number of single double bonds. And I have a difference in stability. Okay, so we will talk on Wednesday about how we can determine which one is more stable. So the part of section 4 that you need to know for your quiz is about the resonance structure. So I want to take the last couple minutes of class just to make sure that we've wrapped up the expanded octet and then talk about the third exception, which is free radicals. The last exception is free radicals. Now, free radicals, I will never have you draw because you cannot satisfy the octet. So let's take a look at nitrogen dioxide. Okay, nitrogen dioxide has how many valence electrons? 17. So remember, one of the things that I told you when you were counting electrons is you should always get to an even number. If you didn't, there should be a charge. Is there a charge on here? No. So this is a free radical. Free radical is a very unstable molecule, meaning it's likely to change. It is high energy. It wants to gather another electron, or at least give up one of its electrons so that all the electrons are paired. But they're not paired in this particular molecule. So if I were to try and draw the dot structure, I wouldn't be able to have an octet around each atom. So I have 17 electrons. Oops. And if we try and draw the dot structures for each of those, it just wouldn't work out. Okay? So I will not ask you to draw a dot structure for a free radical, but I might ask you, multiple choice questions, which one of these is a free radical? And you have to count the electrons in the formulas. Or I might say, which exception to the octet rule does this one follow? And if you count it up and it has an odd number, then you would pick the multiple choice that said free radical. I might say, which one of these is highly reactive? Okay, so you need to know it's highly reactive. You need to associate it with odd electrons. All right, so looking to Wednesday, we will be looking at formal charges. So you probably want to take a look at that. We will do the quiz at the end of class. So we'll go over formal charges before the quiz, but formal charges will not be on the quiz. Okay.